Let's talk about ideal reactors. With the emergence of coronavirus, many people are very interested in disinfection. Especially in schools and workplaces, a lot of money is being spent on different disinfection methods. How do you know how effective a method is? How do you predict if it will work in practice? In fact, several companies have started marketing products to clean air and surfaces. I want to show you one example of a type of product. This particular product uses a fan that pulls air up towards the ceiling. The fan then shines like UV light on the ceiling, disinfecting the air above the fan. This company claims to kill 99.9% of the virus that causes the disease COVID-19. So what I want to do is I want to show you how you can use mass balance to determine if something like this would be adequate for your space. After watching this video, you should understand what an ideal reactor is and that you can use ideal reactors to make relatively simple system models. I also want you to know the assumptions made for the following ideal reactors. So we have completely mixed batch reactors, or CMBRs, completely mixed flow reactors, CMFRs, and then plug flow reactors, PFRs. So going back to our example, this particular fan moves air up and shines this disinfecting light above the fan. I've come up with some reasonable numbers for the sake of this problem. So let's say the fan is able to move 5,000 CFM, cubic feet of air per minute, through this disinfection zone. And that disinfection zone kills 99.9% of the viruses moving through it. Let's say our room is 2,000 cubic feet and one person with COVID-19 enters the room, shedding SARS-CoV-2 particles at a rate of 3,000 particles per minute. What would the steady state virus particle concentration be in the room? We can use mass balance to solve this problem. First, let's consider the mass balance equation. We have accumulation equals inputs minus outputs plus generation minus consumption. First, let's eliminate some terms. Because we're looking for the steady state virus particle concentration, we'll eliminate the accumulation term. Although you may choose to think about the problem a different way, I'll consider the air pulled up into the fan an output and the air recirculating back into the room from the fan as an input. I'm going to assume that there's no other ventilation in the room, and I'll eliminate the generation and consumption terms because I've dealt with the fan using those input and output terms. We have another input, which is the person shedding virus particles. I'm also going to use N instead of M because we're dealing with a number of virus particles, not the mass of virus. So here we have 0 equals N dot for the inputs minus N dot for the outputs. And then we can break our input term further up into inputs from the fan and inputs from the person. Finally, we're going to assume that our system is an ideal system. This means that the system is completely mixed and the concentration of virus particles is the same in every single part of the room. This concentration is going to be CSS, which is going to be the steady state concentration of virus particles in the room. And this is going to be a number of particles per cubic foot. So again, this subscript SS denotes steady state, which is what the problem has asked for. The ideal reactor assumption makes the problem easier to solve, and it's going to give us a rough approximation for what the answer really is. So from our problem statement, we know that N dot input from one person is going to be 3,000 per minute. We have to take the air flow rate in the steady state virus particle concentration into account to calculate the output from the fan N dot. And so what we're going to do is we're just going to multiply that flow rate by the concentration in the room. So this is coming back to another ideal reactor assumption, right? So the concentration in the room equals the concentration coming out of the room. We know the fan inactivates 99.9% of the virus particles, so we can say that the input from the fan is the flow rate 5,000 cubic feet per minute times 0.0001 times that concentration. So we're basically taking that, removing that 99.9%, and what we're left with is 0.1% of that steady state virus particle concentration. We're going to put all of this together and solve for CSS. And what happens is we end up with CSS equals 0.6 virus particles per cubic foot. This might be good enough to prevent infection. That's going to depend on the breathing rate of the person that might be infected and how long they're in the room. And then it also needs to take into account how many virus particles it takes for the person to be infected. That's called the infectivity of a virus. So is this a perfect solution? No. Okay, as I showed you in the picture before, the fan pulls air up and then pushes it out back into the room. It's very likely that the room is not completely mixed, and therefore our number is not completely accurate. However, we can do an analysis like this to get a good idea of how well the fan will work in our situation. So this is an example of one ideal reactor system and how you could use it to solve a problem. Ideal reactors are used by engineers to make estimates and begin a reactor design. They can also be used to model natural systems. While they're not perfect, they are a good starting point, and non-ideal reactor analysis, which we are not covering in this class, is based on the properties of these ideal reactors. So they need to be something So there's something you need to be quite familiar with. There are three main types of ideal reactors. These are completely mixed batch reactors, or CMBRs, completely mixed flow reactors, or CMFRs, and plug flow reactors, or PFRs. So completely mixed batch reactors have no inflows or outflows because they're a batch system. It's also assumed that all of the conditions, concentration, temperature, pressure, etc., are the same throughout the system. They have no dead spaces where perfect mixing would not occur. Completely mixed flow reactors, or CMFRs, are also called completely stirred tank reactors, or CSTRs. So you might see either one of those acronyms. They're flow reactors, so they have inflows and outflows, and they have identical concentrations throughout the system. So whatever is coming out of the system is exactly the same as whatever is in the system. So in our example, we assumed that our room with a fan was a CMFR. Plug flow reactors, PFRs, have no dispersion or mixing along their length. There's no short circuiting. It's assumed that while there's complete mixing within a small volume traveling through a PFR, the volume doesn't mix with any of the volumes before or after it. You can consider these assumptions with ideal reactors while thinking about which types of systems might be modeled as one of them: CMBR, CMFR, or PFR. Systems like stirred tanks with no inflows or outflows, like closed bottles or a closed room, might be modeled as a CMBR. Systems with flow through them, like rooms with ventilation, air above a city, or lakes with water flowing through them, might be modeled as a CMFR. And systems with little mixing and a high aspect ratio, like a river or a pipe, might be modeled as a PFR. Using ideal reactors to model one of these types of systems can give you interesting insights into how these systems might react under different circumstances. So now that you've seen this video, you should understand what an ideal reactor is, and that you can use ideal reactors to make relatively simple system models. And you should also be able to list the assumptions made in the following ideal reactors: completely mixed batch reactors, or CMBRs, completely mixed flow reactors, CMFRs, and plug flow reactor, PFR.